Imagine our universe as a vast cosmic ocean. We see the stars, the galaxies, the radiant light. But what if I told you that over 90% of this ocean is made up of something we can't directly see or touch? This missing component, often called dark energy or dark matter, is the universe's greatest mystery, the invisible hand shaping the cosmos as we know it. Its existence challenges our fundamental understanding of physics, forcing us to question everything we thought we knew about space and time. This enigmatic energy is not just a small anomaly. It's the dominant force driving the accelerated expansion of the universe, a phenomenon that has baffled scientists for decades. Why is the universe expanding faster and faster? What is this unseen energy that defies detection? Today, we embark on a journey to explore 30 groundbreaking theories that attempt to unlock the secrets of this missing energy, from the bizarre implications of phantom energy to the mind-bending possibility of extra dimensions. Each theory offers a unique perspective, a potential key to solving this cosmic puzzle. Join us as we delve into the heart of the unknown, where the quest to understand dark energy could reveal the true nature of our universe and our place within it. Prepare to have your perception of reality challenged as we explore the frontiers of cosmology and the ongoing scientific revolution that seeks to illuminate the darkest corners of the cosmos. Our first stop, we will discuss the cosmological constant. Now, let's turn our attention to one of the leading explanations, the cosmological constant. Imagine that empty space itself isn't truly empty, but rather possesses an inherent energy. This energy, uniformly distributed throughout the universe, exerts a negative pressure, pushing the fabric of space outward. The cosmological constant, often denoted by the Greek letter lambda, represents this intrinsic energy density of the vacuum of space. Its origin lies in quantum field theory, which posits that even in the emptiest void, virtual particles constantly pop in and out of existence, creating a seething quantum foam. These fleeting particles contribute a certain amount of energy to space, leading to the idea of a non-zero cosmological constant. However, here's where the trouble begins. When scientists calculate the expected value of the cosmological constant based on quantum field theory, the result is astronomically larger. Some estimations say 120 orders of magnitude than what we observe through cosmological measurements. This enormous discrepancy is known as the cosmological constant problem, one of the biggest unsolved mysteries in modern physics. Why is the observed value of dark energy so incredibly small compared to what theory predicts? Is there something fundamentally wrong with our understanding of quantum field theory? Or is there some unknown mechanism that cancels out most of this vacuum energy? Despite this profound issue, the cosmological constant remains a key component of the lambda-CDM model, which is our current standard model of cosmology. Lambda-CDM, where CDM stands for cold dark matter, successfully explains many observed features of the universe, such as the cosmic microwave background, the large-scale structure of galaxies, and the accelerated expansion. In this model, the cosmological constant accounts for about 70% of the universe's total energy density, making it the dominant form of dark energy. While the cosmological constant offers a simple and elegant explanation for dark energy, the cosmological constant problem casts a long shadow, suggesting that our understanding of the universe is far from complete. As we continue our journey into the unknown, we now set our sights on quintessence, another compelling theory in the quest to understand the universe's missing energy. The second theory, quintessence, presents a more dynamic picture, quite different from the static cosmological constant. Quintessence proposes that dark energy isn't a constant, unvarying energy density inherent to space, but rather a dynamic, time-evolving field that permeates the universe. Think of it like a cosmic chameleon, adapting its properties over time and space. In essence, quintessence is modeled as a scalar field, similar to the Higgs field, which is associated with the Higgs boson. This scalar field possesses a potential energy, and it's this potential energy that drives the accelerated expansion of the universe. Unlike the cosmological constant, where the energy density remains constant, quintessence's energy density can change over cosmic time. This opens up a range of possibilities for how dark energy might have behaved in the past and how it will evolve in the future. One intriguing aspect of quintessence is that it could potentially interact with other forms of matter and energy in the universe, such as dark matter or even ordinary matter. These interactions, if they exist, could leave subtle imprints on the cosmic microwave background or the large-scale distribution of galaxies, providing clues to the nature of quintessence. However, detecting these interactions observationally is a major challenge. Because quintessence is dynamic, its properties are constrained by observational data. Cosmologists use various methods such as measuring the expansion rate of the universe at different epochs, studying the distribution of galaxies, and analyzing the cosmic microwave background to put limits on quintessence's equation of state, which describes the relationship between its pressure and energy density. These observations help to narrow down the range of viable quintessence models and test their consistency with the observed cosmic acceleration. The search for observational evidence of quintessence continues, pushing the boundaries of our understanding of dark energy and the universe's fate. As we probe deeper into the mysteries of the cosmos, our next stop is modified Newtonian dynamics, or MOND, an intriguing approach that challenges our conventional understanding of gravity itself. The third theory, modified Newtonian dynamics, often shortened to MOND, offers a bold departure from the standard cosmological model. Instead of invoking dark matter and dark energy to explain the universe's mysteries, MOND proposes a modification to Newton's law of gravity at very low accelerations. Imagine stepping into a world where gravity behaves differently than we expect. MOND suggests that at extremely small accelerations, such as those experienced by stars on the outskirts of galaxies, gravity becomes stronger than what Newton's law predicts. This seemingly simple modification can have profound consequences. One of the most compelling successes of MOND is its ability to explain the observed rotation curves of galaxies without the need for dark matter. When we observe how fast stars are orbiting within a galaxy, we find that they move much faster than expected based on the visible matter alone. This discrepancy is usually attributed to the presence of dark matter, which is thought to provide the extra gravitational pull needed to keep the stars from flying apart. However, MOND offers an alternative explanation. By modifying gravity at low accelerations, MOND can account for the observed rotation curves without invoking any additional unseen matter. It's as if gravity itself is behaving differently in these galactic environments, providing the extra glue needed to hold galaxies together. Despite its successes in explaining galactic rotation curves, MOND faces challenges when applied to larger cosmological phenomena. For example, it struggles to fully account for the observed structure formation in the universe or the anisotropies in the cosmic microwave background. These observations are well explained by the lambda-CDM model, which includes both dark matter and dark energy. Moreover, MOND lacks a complete and consistent theoretical framework that can be seamlessly integrated into a cosmological context. While it provides a useful phenomenological description of gravity at galactic scales, it doesn't offer a fundamental explanation for why gravity should be modified in this way. This has led to efforts to develop relativistic versions of MOND, such as tensor vector scalar gravity, or TVS, which attempt to embed MOND within a more complete theoretical framework that is compatible with general relativity. However, these theories are still under development and face their own challenges. As we continue our exploration, let's now turn our attention to modified gravity theories, which represent another class of approaches that seek to explain cosmic acceleration without invoking dark energy. Transitioning from alterations within Newtonian physics, another avenue of exploration involves tweaking Einstein's theory of general relativity itself. Modified gravity theories such as F of R gravity and Horndeski theory represent such attempts to explain cosmic acceleration without invoking dark energy. Instead of adding new components to the universe, these theories propose changes to the fundamental laws governing gravity. Imagine gravity not as a fixed entity described perfectly by Einstein's equations, but as a more flexible phenomenon that can be altered at large scales. These modified gravity theories do just that. They modify the Einstein-Hilbert action, which is the foundation of general relativity, to include additional terms that become significant only at cosmological distances. For example, F of R gravity replaces the Ricci scalar R in the Einstein-Hilbert action with a more general function of R, denoted as F of R. This seemingly small change can lead to significant modifications in the behavior of gravity at large scales, potentially explaining the observed cosmic acceleration. One of the key goals of modified gravity theories is to provide a unified explanation for both dark matter and dark energy effects. In some models, the modifications to gravity can mimic the effects of dark matter on galactic scales, while also driving the accelerated expansion of the universe. This would eliminate the need for two separate, mysterious components and offer a more elegant and parsimonious description of the cosmos. However, constructing viable modified gravity theories is a challenging task. The theories must not only explain the observed cosmic acceleration, but also be consistent with a wide range of observational constraints. These include tests of general relativity on smaller scales, such as those performed in the solar system, as well as cosmological observations like the cosmic microwave background and the large-scale structure of the universe. To test these theories, scientists look for deviations from the predictions of general relativity. This involves carefully analyzing the motion of galaxies, the bending of light around massive objects, and the expansion history of the universe. Observational tests play a crucial role in constraining the parameter space of modified gravity theories and determining whether they are a viable alternative to the standard cosmological model. As research continues, we'll now consider dark fluid models, an approach that seeks to unify dark matter and dark energy into a single, exotic substance. Now, shifting gears to explore a more unified perspective, we turn our attention to dark fluid models. These models propose an intriguing solution by treating dark matter and dark energy not as separate entities, but as a single fluid with exotic properties. Imagine a substance that behaves like dark matter on galactic scales, providing the extra gravity needed to explain the observed rotation curves of galaxies, and simultaneously acts as dark energy on cosmological scales, driving the accelerated expansion of the universe. That is the essence of dark fluid models. The allure of dark fluid models lies in their ability to offer a more streamlined explanation of the cosmos. Instead of postulating two distinct and mysterious components, dark matter and dark energy, these models suggest that a single exotic fluid can account for both phenomena. This fluid would possess an unusual equation of state, a relationship between its pressure and density, that allows it to mimic the effects of both dark matter and dark energy under different conditions. At high densities typical of galactic environments, the fluid would behave like pressure-less dark matter, while at low densities prevalent on cosmological scales, it would exert negative pressure characteristic of dark energy. However, formulating a stable and physically plausible dark fluid is no easy feat. The equation of state must be carefully constructed to avoid violating fundamental physical principles, such as the speed of sound remaining below the speed of light. Furthermore, the model must be stable against perturbations. Otherwise, any small density fluctuations could grow uncontrollably, leading to undesirable cosmological consequences. These challenges have led to a variety of proposed dark fluid models, each with its own unique equation of state and set of parameters. Observational constraints play a crucial role in winnowing down these models and determining which, if any, are viable descriptions of the universe. Data from the cosmic microwave background, large-scale structure surveys, and supernova observations all provide valuable information about the properties of dark fluids, helping to constrain their equation of state and assess their compatibility with the observed universe. As we continue our search for answers, we next confront the strange possibility of phantom energy, a form of dark energy with even more bizarre implications. Transitioning into even stranger realms of possibility, we now consider phantom energy. This is a particularly unsettling form of dark energy. Phantom energy distinguishes itself with an equation of state parameter less than -1, a value that defies conventional understanding. This seemingly small difference has monumental consequences, suggesting that the expansion of the universe is not just accelerating, but super-accelerating, growing at an ever-increasing rate. The theoretical implications of phantom energy are nothing short of apocalyptic. Unlike the more benign models of dark energy, where the universe expands indefinitely but remains intact, phantom energy raises the specter of a Big Rip singularity. In this scenario, the super-acceleration driven by phantom energy becomes so intense that it overcomes all forces holding matter together. Galaxies would be torn apart, followed by solar systems, planets, and eventually even atoms, as the universe rips itself apart in a final, dramatic act of cosmic self-destruction. The time scale for this big rip depends on the exact value of the equation of state parameter for phantom energy. However, even within the bounds of current observations, the possibility remains a chilling reminder of the potential instability of our universe. The existence of phantom energy is far from certain, and observational evidence remains inconclusive. While some data from supernova surveys and cosmic microwave background observations have hinted at the possibility of an equation of state parameter less than -1, these results are often within the margin of error and subject to alternative interpretations. Many scientists remain skeptical, as phantom energy poses significant theoretical challenges, including violations of energy conditions and the need for exotic physics beyond the standard model. Despite the uncertainty, the phantom energy scenario serves as a valuable reminder of the vastness of our ignorance and the need for continued exploration in the quest to understand the universe's ultimate fate. As we continue our exploration, we will next look at how Chaplygin gas relates to dark matter and dark energy, transitioning now from the potentially universe-ending implications of phantom energy. We turn our attention to a more unifying, albeit still exotic, concept, the Chaplygin gas. The Chaplygin gas emerges as an intriguing contender in the quest to understand dark matter and dark energy, not as separate entities, but as unified aspects of a single, exotic fluid. This theoretical substance exhibits a chameleon-like behavior, adapting its properties in response to the prevailing density of the universe. At high densities, the Chaplygin gas mimics the behavior of dark matter, exerting gravitational pull and contributing to the formation of cosmic structures like galaxies and galaxy clusters. In this state, it acts much like ordinary matter, slowing down the expansion of the universe through its gravitational effects. However, as the universe expands and the density of matter decreases, the Chaplygin gas undergoes a transformation, morphing into a form of dark energy that drives the accelerated expansion. In this low-density regime, it exerts negative pressure, pushing the fabric of space outward and counteracting the attractive force of gravity. This dual nature allows the Chaplygin gas to potentially unify the roles of dark matter and dark energy into a single component, simplifying the cosmological model and offering a more elegant explanation for the observed cosmic phenomena. The behavior of Chaplygin gas is governed by a specific equation of state that relates its pressure to its density. This equation of state is characterized by a parameter that determines the relative contributions of the dark matter-like and dark energy-like behaviors. By carefully tuning this parameter, it is possible to match the observed abundance of dark matter and the observed rate of cosmic acceleration, providing a possible solution to the missing energy problem. However, the Chaplygin gas model is not without its challenges. Observational constraints from cosmic microwave background data and large-scale structure surveys have placed stringent limits on the properties of the Chaplygin gas, requiring fine-tuning of its parameters to avoid conflicts with observations. Furthermore, some theoretical studies have raised concerns about the stability and physical plausibility of the Chaplygin gas model, questioning its ability to form stable structures and avoid unphysical behavior. Despite these challenges, the Chaplygin gas remains an active area of research, with ongoing efforts to refine the model and test its predictions against new observational data. Future experiments and surveys, such as those probing the distribution of galaxies and the properties of the cosmic microwave background, will provide crucial tests of the Chaplygin gas hypothesis and help to determine whether it can truly unify dark matter and dark energy into a single, elegant framework. Having now looked at Chaplygin gas, we will next explore how extra dimensions might influence gravity at large scales. Now, venturing into even more speculative territory, let's consider the possibility of extra dimensions and their subtle yet profound influence on the cosmos. The theory of extra dimensions proposes that our universe may have more than the three spatial dimensions we readily perceive. These additional dimensions, often curled up at subatomic scales, could have far-reaching consequences for gravity and the nature of dark energy. The existence of extra dimensions can modify general relativity, Einstein's theory of gravity at large scales. In these scenarios, gravity can leak into the extra dimensions, weakening its strength in our observable universe. This weakening of gravity can mimic the effects of dark energy, leading to the accelerated expansion of the universe without the need for any exotic form of energy. The extra dimensions warp space-time in a way that introduces new terms into Einstein's equations, effectively creating a dark energy component. One prominent model involving extra dimensions is the Randall-Sundrum scenario. This model proposes that our universe is a three-dimensional brane embedded in a higher dimensional space-time. In this framework, gravity is strong in the higher dimensional space-time, but weak on our brane due to the curvature of the extra dimensions. This can explain why gravity is so much weaker than the other fundamental forces, such as electromagnetism, and can also lead to an effective dark energy component that drives the accelerated expansion of the universe. The search for extra dimensions is an active area of experimental research. High-energy particle colliders, like the Large Hadron Collider at CERN, are searching for evidence of extra dimensions by looking for missing energy or the production of new particles that can only exist in extra dimensions. Gravitational wave observations, such as those made by the Laser Interferometer Gravitational Wave Observatory and Virgo collaborations, may also provide clues about the existence of extra dimensions. The detection of primordial gravitational waves or modifications to the propagation of gravitational waves over cosmic distances could provide evidence for extra dimensions and their influence on gravity. As we contemplate extra dimensions, we'll next examine backreaction, a theory suggesting cosmic expansion arises from the averaging of local inhomogeneities in the universe. The ninth theory, backreaction, offers a fascinating perspective, suggesting that the universe's accelerated expansion isn't driven by mysterious dark energy, but rather by the complex interplay of cosmic structures. In this view, the universe isn't perfectly uniform as often assumed in simplified models. Instead, it's a tapestry of dense regions like galaxies and voids, vast empty spaces. The nonlinear evolution of cosmic structures driven by gravity can create an effective dark energy component. As matter clumps together to form galaxies and clusters, the expansion of the underdense regions, the voids, accelerates relative to the denser regions. Averaging these local inhomogeneities across the entire universe leads to a net acceleration that mimics the effects of dark energy. This backreaction from the growth of structures alters the overall expansion rate, potentially explaining the observed acceleration without needing to invoke any new form of energy. Calculating backreaction effects presents significant mathematical challenges. The equations governing the evolution of cosmic structures are highly nonlinear, making it difficult to obtain exact solutions. Approximations and numerical simulations are often used to estimate the magnitude of backreaction effects, but these methods can be computationally expensive and may introduce uncertainties. Understanding the precise impact of backreaction requires a detailed understanding of the distribution of matter in the universe and the complex interplay of gravitational forces. Observational evidence for or against the significance of backreaction remains a topic of ongoing research. While some studies suggest that backreaction could contribute significantly to the observed accelerated expansion, others argue that its effects are too small to account for the total amount of dark energy. Distinguishing the effects of backreaction from those of genuine dark energy requires precise measurements of the expansion rate of the universe, the distribution of matter, and the growth of cosmic structures. Future surveys and observational probes will play a crucial role in testing the backreaction theory and determining its validity as an alternative explanation for the universe's accelerated expansion. Considering these cosmic scale interactions, we will now examine the universe's estimated age and how it impacts the dark energy equation. The 10th theory suggests that the universe is younger than we thought, and this has significant ramifications for the dark energy equation. Recent measurements of the Hubble constant, which describes the rate at which the universe is expanding, have led to a perplexing discrepancy known as the Hubble tension. Different methods of measuring the Hubble constant yield conflicting results. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest a lower value, while measurements based on observations of supernova and other local phenomena indicate a higher value. If the universe is indeed younger than the age implied by the cosmic microwave background measurements, this could potentially resolve the Hubble tension. A younger universe would imply a faster expansion rate, bringing the cosmic microwave background measurements into closer agreement with the local measurements. One potential explanation for a younger universe involves modifications to our understanding of dark energy. If dark energy's properties have evolved over time, rather than remaining constant as assumed in the standard lambda CDM model, this could affect the expansion history of the universe and reconcile the conflicting measurements of the Hubble constant. However, a younger universe also presents new problems. It could challenge our understanding of the formation and evolution of galaxies and other cosmic structures. If the universe is younger, there would be less time for these structures to form, potentially requiring adjustments to our models of structure formation. Moreover, a younger universe might necessitate revisions to our understanding of the properties of dark matter and other fundamental parameters of the cosmos. As we consider the age of the universe, let's question if the vacuum state of the universe is unstable and will eventually tunnel to a lower energy state. The 11th theory delves into vacuum decay, exploring the concept that the universe's current vacuum state might not be as stable as we assume. The vacuum state in particle physics refers to the state of lowest possible energy. However, it's theorized that our universe might be residing in a false vacuum, a state that is seemingly stable but not truly the lowest energy configuration. Imagine a ball resting in a shallow depression on a hillside. It appears stable, but a nudge could send it rolling down to a lower point. Similarly, our universe could, at any moment, tunnel to a lower energy state. This tunneling process is a quantum phenomenon where a particle can pass through an energy barrier even if it doesn't have enough energy to go over it. If a region of space were to undergo vacuum decay, it would create a bubble of true vacuum that expands at nearly the speed of light. The energy difference between the false vacuum and the true vacuum is enormous, and the consequences of such an event would be catastrophic. Everything within the expanding bubble would be fundamentally altered, as the laws of physics and the constants of nature could be different in the true vacuum state. The possibility of vacuum decay raises profound questions about the ultimate fate of the universe. While the probability of such an event occurring is currently believed to be extremely low, it's not zero. Scientists are actively researching the properties of the Higgs boson and other fundamental particles to better understand the stability of the vacuum state. If vacuum decay were to occur, it would not only destroy our universe but also potentially trigger the decay of other regions of the multiverse, if such a concept exists. Now, shifting our focus slightly, what if there exists a mirror universe with opposite physics, exerting a gravitational pull on our own, causing it to expand? The 12th theory turns to mirror universes, suggesting that a cosmos with physics opposite to our own could be exerting a gravitational pull, thereby contributing to the observed expansion. Imagine a universe where fundamental laws, like the direction of time or the charge of particles, are reversed compared to ours. This mirror universe wouldn't just be a reflection in terms of spatial arrangement, but would possess fundamentally different physical properties. One intriguing idea is that the Big Bang might have created not only our universe but also its mirror counterpart. This other universe could exist in a sort of parallel reality, interacting with our own through gravity. The concept arises from certain cosmological models that allow for the existence of universes with different properties emerging from the same initial event. If such a mirror universe exists, it could be subtly influencing our own. Its gravitational pull, acting across vast cosmic distances, might account for some of the unexplained acceleration in the expansion of our universe. Detecting such a mirror universe poses a significant challenge, however. Because it's defined by opposite physics, it might not interact with our universe through conventional means like electromagnetic radiation. Evidence for a mirror universe could potentially be observed through very subtle gravitational effects that cannot be explained by the standard model of cosmology. Scientists might look for anomalies in the cosmic microwave background, the afterglow of the Big Bang, or in the distribution of large-scale structures in the universe. Alternative, researchers may focus on searching for unique gravitational wave signatures that standard physics cannot explain. These gravitational waves could act as messengers from the mirror universe, providing insights into its properties and its influence on our cosmos. As we consider the potential influence of actions to the nature of dark matter and dark energy, we find ourselves at the threshold of yet another intriguing hypothesis. Transitioning into the realm of theoretical physics, the 13th theory introduces actions, hypothetical elementary particles that might just solve the riddle of both dark matter and dark energy. Actions are incredibly light, neutral particles that were originally proposed to resolve a different problem in particle physics related to the strong nuclear force. However, their properties make them excellent candidates for dark matter. Because they are so light and weakly interacting, actions could have been produced in large quantities in the early universe without clumping together like ordinary matter. This would allow them to form a diffuse background of dark matter that pervades the cosmos. The idea that actions could constitute dark matter has garnered significant attention, leading to numerous experimental efforts to detect them. These experiments typically involve searching for the faint electromagnetic signals that actions are predicted to produce under certain conditions. If actions make up dark matter, they could also indirectly affect the behavior of galaxies and other cosmic structures, offering another avenue for detection through astrophysical observations. But how might actions contribute to dark energy, the mysterious force driving the accelerating expansion of the universe? One intriguing possibility is that a sea of extremely light actions could generate a form of quintessence, a dynamic field that acts as dark energy. The energy density of this action field would depend on its mass and abundance, as well as its interactions with itself and other particles. If the properties of these actions are finely tuned, they could produce an energy density that matches the observed value of dark energy. Moreover, because actions are fundamental particles with well-defined properties, studying them could provide valuable insights into the nature of dark energy and its evolution over cosmic time. Scientists are actively exploring various theoretical and experimental approaches to probe the properties of actions and test their potential role as both dark matter and dark energy. These efforts could ultimately unveil the true nature of these elusive particles and shed light on some of the biggest mysteries in cosmology. Our journey now takes us to the world of weakly interacting massive particles, or WIMP, another potential key to unlocking the secrets of dark matter and dark energy. Now, shifting our focus to another set of promising candidates, we arrive at the theory of weakly interacting massive particles, or WIMP. These particles have long been considered prime suspects for dark matter, and their potential role in dark energy is also being explored. WIMP are hypothetical particles that interact through the weak nuclear force and gravity, but only feebly with ordinary matter. This weak interaction explains why they have eluded direct detection so far, but it also makes them abundant in the universe. According to the theory, WIMP were produced in large quantities in the early universe when temperatures were extremely high. As the universe expanded and cooled, WIMP would have annihilated each other, reducing their overall abundance. However, because their interactions are weak, some WIMP would have survived this annihilation process, leaving behind a residual density that matches the observed amount of dark matter. The search for WIMP is a major focus of experimental efforts worldwide. Many experiments are designed to detect the rare collisions between WIMP and ordinary matter particles within detectors. These detectors are typically located deep underground to shield them from cosmic rays and other background radiation. When a WIMP collides with an atom in the detector, it can deposit a small amount of energy that can be measured. While no definitive detection has been made yet, these experiments have set increasingly stringent limits on the properties of WIMP, guiding theoretical models and narrowing down the range of possible masses and interaction strengths. But how might WIMP contribute to dark energy in addition to their role as dark matter? One speculative idea involves the possibility that WIMP could interact with a hidden sector of particles and forces beyond the standard model of particle physics. These interactions could give rise to a form of dark energy that is dynamic and evolving, similar to quintessence. Alternatively, WIMP could decay into lighter particles, releasing energy that contributes to the accelerated expansion of the universe. While these ideas are still highly theoretical, they highlight the potential for WIMP to play a dual role in the dark universe, influencing both the matter distribution and the expansion rate. As scientists continue to explore the properties of WIMP and search for their elusive signals, we may uncover new clues about the nature of dark energy and its connection to the broader landscape of particle physics. With these concepts in mind, our investigation proceeds to the realm of sterile neutrinos as we peel back more layers of the universe's mysteries. Now, venturing further into the enigmatic realm of particle physics, we arrive at the tantalizing theory of sterile neutrinos. The possibility of a parallel neutrino world and its profound impact on both dark matter and dark energy. Sterile neutrinos are hypothetical particles that, unlike the three active neutrinos we know, do not interact through the weak nuclear force. This absence of interaction makes them sterile to the standard model forces, interacting only through gravity and possibly through mixing with active neutrinos. The concept of sterile neutrinos arises from anomalies observed in neutrino oscillation experiments. These experiments, which study how neutrinos change flavor as they travel, have hinted at the existence of additional neutrino states beyond the three known ones. If sterile neutrinos exist, they could mix with active neutrinos, leading to observable effects in oscillation patterns. Moreover, their existence could have far-reaching implications for understanding the nature of dark matter and dark energy. One compelling idea is that sterile neutrinos themselves could constitute a portion of the dark matter in the universe. If they have masses in the kiloelectronvolt range, they would be warm dark matter candidates, which could help explain the observed distribution of galaxies and alleviate some of the small-scale structure problems associated with cold dark matter models. Alternatively, sterile neutrinos could indirectly influence dark energy through their interactions with other particles in a hidden sector. These interactions could generate a form of dark energy that is dynamic and evolving, contributing to the accelerated expansion of the universe. The search for sterile neutrinos is an active area of research, with experiments designed to detect their mixing with active neutrinos and to probe their potential role as dark matter candidates. These experiments involve studying neutrino oscillations at short baselines, searching for decays of sterile neutrinos into observable particles, and looking for signatures of sterile neutrino dark matter in astrophysical observations. As scientists continue to push the boundaries of neutrino physics, we may soon uncover decisive evidence for the existence of sterile neutrinos and their role in shaping the dark side of the universe. What secrets might gravitational waves hold? Now, shifting our focus to the ripples in spacetime itself, gravitational waves offer a unique window into the universe and might unveil some of dark matter and dark energy's properties. Gravitational waves are disturbances in the curvature of spacetime, generated by accelerating massive objects. These waves propagate through the cosmos at the speed of light, carrying information about their sources, such as colliding black holes or neutron stars. The detection of gravitational waves by experiments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo has opened up new avenues for studying the universe. These observations not only confirm Einstein's theory of general relativity, but also provide insights into astrophysical phenomena that are otherwise invisible to traditional telescopes. Gravitational waves can probe regions of spacetime that are obscured by dust or gas, allowing scientists to study black holes, neutron stars, and other exotic objects in unprecedented detail. One intriguing possibility is that gravitational waves could provide clues about the nature of dark matter and dark energy. For example, the presence of dark matter could affect the propagation of gravitational waves, causing them to bend or scatter as they travel through the universe. By carefully analyzing the waveforms of gravitational waves from distant sources, scientists may be able to detect these subtle effects and infer the distribution of dark matter along the line of sight. Additionally, gravitational waves could be generated by phase transitions in the early universe, which might be related to the origin of dark energy. Future gravitational wave observatories, such as the Einstein Telescope and the Cosmic Explorer, promise to be even more sensitive and capable of detecting weaker gravitational waves from more distant sources. These advanced detectors will enable scientists to probe the universe at earlier epochs, closer to the Big Bang, and to study a wider range of astrophysical phenomena. By combining gravitational wave observations with data from traditional telescopes and particle physics experiments, scientists hope to unravel the mysteries of dark matter and dark energy and gain a deeper understanding of the fundamental laws of nature. Could it be that the inflationary epoch remnants contain insight? Venturing further into the dawn of time, the inflationary epoch might hold the key. The inflationary epoch is a period of accelerated expansion in the very early universe, occurring fractions of a second after the Big Bang. During this brief but crucial period, the universe expanded exponentially, stretching from subatomic scales to macroscopic sizes in an incredibly short amount of time. This rapid expansion is believed to have smoothed out the universe, flattened its geometry, and seeded the initial conditions for the formation of galaxies and large-scale structures. Now, some theories propose that the inflationary epoch may have left behind remnants of energy that could contribute to dark matter and dark energy. One possibility is that the energy driving inflation did not completely dissipate after inflation ended, leaving behind a residual amount of vacuum energy that permeates the universe. This residual energy could act as a cosmological constant, contributing to the accelerated expansion of the universe observed today. Another idea is that the inflationary epoch may have generated a network of topological defects, such as cosmic strings or domain walls, which could contribute to the energy density of the universe. These defects are relics of phase transitions that occurred during inflation and could have survived to the present day, exerting a gravitational influence on the surrounding matter and energy. Furthermore, the inflationary epoch may have produced a spectrum of primordial gravitational waves, which could also contribute to the energy density of the universe. These gravitational waves would have been generated by quantum fluctuations during inflation and would have stretched to macroscopic scales as the universe expanded. Although these primordial gravitational waves have not yet been directly detected, their existence is predicted by many inflationary models, and future experiments may be able to observe them, providing valuable insights into the nature of inflation and its potential connection to dark energy. These relics from the inflationary epoch offer a tantalizing glimpse into the early universe and may hold clues about the origin of dark matter and dark energy. The study of these remnants requires a combination of theoretical modeling and observational searches, pushing the boundaries of our understanding of cosmology and fundamental physics. As we explore the aftermath of this rapid expansion, the fifth force may be the key to understanding it. As we consider the possibilities, the concept of a fifth fundamental force emerges as a potential game changer. The universe, as we currently understand it, operates under the influence of four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. However, some theories propose the existence of a fifth force that could be responsible for some of the unexplained phenomena in the cosmos, including dark matter and dark energy. This hypothetical force would interact with matter and energy in ways that differ from the known forces, potentially mediating interactions between particles that are not affected by the other four forces. One possibility is that the fifth force interacts with dark matter particles, providing a mechanism for dark matter to interact with itself or with ordinary matter. This interaction could explain some of the observed properties of dark matter, such as its distribution in galaxies and galaxy clusters. For example, if dark matter particles interact through a fifth force, they could scatter off each other, leading to a more even distribution of dark matter in the inner regions of galaxies. Another idea is that the fifth force mediates interactions between dark energy and ordinary matter, providing a way for dark energy to influence the expansion of the universe. This interaction could explain why the observed value of dark energy is so much smaller than theoretical predictions, as the fifth force could counteract the effects of dark energy on cosmic scales. Furthermore, the fifth force could manifest itself as a modification of gravity at large distances, leading to deviations from Einstein's theory of general relativity. These deviations could explain the accelerated expansion of the universe without the need for dark energy, as the fifth force could effectively mimic the effects of a cosmological constant. Experimental searches for the fifth force are ongoing, with scientists looking for subtle deviations from the known laws of physics that could indicate its existence. These searches include precision measurements of gravity, tests of the equivalence principle, and searches for new particles that could mediate the fifth force. The exploration of this potential fifth force guides us to the next theory of dark radiation and how relativistic particles may be the cause of dark matter and dark energy. Turning our attention towards another intriguing possibility, we consider the role of dark radiation, where relativistic particles may be the cause of dark matter and dark energy. Dark radiation refers to any hypothetical form of radiation that interacts very weakly with ordinary matter and radiation, making it difficult to detect directly. These particles are relativistic, meaning they travel at or near the speed of light and have very little mass. One candidate for dark radiation is sterile neutrinos, which are hypothetical particles that interact only through gravity and possibly the weak force, but not through the electromagnetic or strong force. Sterile neutrinos are heavier than the known neutrinos, but still much lighter than other elementary particles. The existence of dark radiation could have several important implications for our understanding of the universe. For example, it could contribute to the total energy density of the universe, affecting the expansion rate and the formation of large-scale structures. If dark radiation interacts with dark matter particles, it could also affect the distribution of dark matter in galaxies and galaxy clusters. The presence of dark radiation can influence the cosmic microwave background, or CMB, which is the afterglow of the Big Bang. By studying the CMB, scientists can place constraints on the amount of dark radiation in the universe and its properties. Current observations suggest that dark radiation makes up only a small fraction of the total energy density of the universe, but its effects could still be significant. Moreover, dark radiation could also help to resolve some of the tensions in cosmology, such as the Hubble tension, which is the discrepancy between the local measurement of the Hubble constant and the value inferred from the CMB. By adding extra radiation to the early universe, the expansion rate could be increased, which could bring the two measurements into better agreement. However, this requires a delicate balance, as too much dark radiation could also lead to other problems, such as disrupting the formation of light elements in the early universe. Searches for dark radiation are ongoing, with scientists using a variety of techniques to try to detect its presence. These include looking for subtle changes in the CMB, searching for new particles at colliders, and studying the properties of neutrinos. These searches aim to shed light on the nature of dark radiation and its role in the universe. That said, our journey through the potential explanations continues as we look at how a varying speed of light in the early universe may affect our understanding of dark energy. Stepping into more speculative realms, let's consider a theory in which the speed of light was not always the constant we know today. The varying speed of light theory, or VSL, proposes that the speed of light was much faster, possibly infinite, in the early universe and has since slowed down to its current value. This idea challenges one of the foundational principles of modern physics, which assumes that the speed of light is constant throughout space and time. The motivation behind VSL theories is to address some of the persistent problems in cosmology, such as the horizon problem and the flatness problem, which are typically solved by invoking the theory of cosmic inflation. The horizon problem arises because the observable universe is remarkably uniform in temperature, even though regions that are now widely separated would not have had time to interact and equilibrate if the speed of light has always been constant. The flatness problem concerns the fine-tuning of the initial conditions of the universe, which must have been incredibly precise to avoid collapsing or expanding too rapidly. By allowing the speed of light to vary, VSL theories can potentially solve these problems without inflation. If the speed of light was much faster in the early universe, distant regions could have been in causal contact, allowing them to equilibrate and become uniform. Additionally, varying the speed of light could affect the geometry of spacetime, potentially resolving the flatness problem. One of the main challenges for VSL theories is to construct a consistent theoretical framework that incorporates the varying speed of light while also being compatible with the well-established laws of physics. This typically involves modifying Einstein's theory of general relativity or introducing new fields and interactions. Furthermore, VSL theories need to make testable predictions that can be compared with observational data. One possible test is to look for variations in the fine structure constant, which is a fundamental constant that determines the strength of electromagnetic interactions. If the speed of light has varied over time, it could also affect the value of the fine structure constant. Another potential test is to look for specific patterns in the cosmic microwave background, or CMB, which could be imprinted by the varying speed of light in the early universe. While there is currently no direct evidence for a varying speed of light, these tests could potentially provide support for the theory. VSL theories remain controversial within the scientific community as they challenge some of the most basic assumptions of physics. However, they also offer a potentially elegant solution to some of the persistent problems in cosmology, and they continue to be an active area of research. Now, preparing to shift our perspective yet again, we will examine how string theory landscapes might provide clues about dark energy. Transitioning from the cosmic scales to the realm of theoretical physics, let's explore how string theory landscapes might provide clues about dark energy. String theory, a theoretical framework that attempts to unify all fundamental forces and particles, predicts the existence of a vast number of possible universes, often referred to as the string theory landscape. Each of these universes could have different physical constants and vacuum energies, leading to a wide range of possible cosmological scenarios. The string theory landscape arises from the many possible ways that the extra dimensions in string theory can be compactified or curled up to form the four-dimensional spacetime that we observe. Each compactification corresponds to a different solution of the string theory equations, with its own set of physical laws and constants. One of the key implications of the string theory landscape is that our universe might have a non-zero vacuum energy which contributes to dark energy. Vacuum energy is the energy of empty space, and it can arise from quantum fluctuations of fields. In string theory, the vacuum energy is determined by the specific compactification of the extra dimensions, and it can be either positive, negative, or zero. If our universe happens to reside in a region of the string theory landscape with a positive vacuum energy, this could explain the observed accelerated expansion of the universe. However, one of the main challenges facing this idea is that the observed value of dark energy is incredibly small compared to the typical scales of string theory. This discrepancy, known as the cosmological constant problem, remains one of the biggest puzzles in theoretical physics. Another challenge is that it is difficult to test string theory predictions observationally due to the high energies and small scales involved. However, there are some potential ways to probe the string theory landscape indirectly, such as by looking for specific patterns in the cosmic microwave background or by searching for new particles predicted by string theory. Additionally, some theorists have proposed that the string theory landscape might be connected to the multiverse, the idea that our universe is just one of many universes that exist. In this scenario, the other universes in the multiverse could have different physical laws and constants, and they could potentially interact with our universe in subtle ways. While the string theory landscape remains a speculative idea, it offers a potentially profound explanation for the nature of dark energy and the origin of our universe. As we continue to explore the mysteries of the cosmos, we'll now consider the impact of time-varying gravity and how it can affect dark energy. Shifting our perspective, let us consider how gravity itself might evolve over time, influencing the behavior of dark energy. The idea that the gravitational constant, often denoted as G, may not be constant has intrigued physicists for decades. Most cosmological models assume that G has remained unchanged throughout the universe's history. However, some theories propose that G could vary with time, which could have significant implications for our understanding of dark energy and the universe's fate. If G were to decrease over time, the gravitational force would weaken, potentially leading to a faster expansion of the universe. This could mimic the effects of dark energy or alter its behavior, making it appear stronger or weaker than it actually is. Conversely, if G were to increase, gravity would become stronger, slowing down the expansion. One way to test whether G is changing is to look at the orbits of planets and other celestial objects. If G were decreasing, for example, the orbits of planets would gradually expand over time. Scientists can use precise measurements of planetary positions to set limits on the rate at which G might be changing. Another approach is to study the cosmic microwave background, which provides a snapshot of the universe in its early stages. Changes in G would affect the expansion rate of the early universe, leaving an imprint on the cosmic microwave background. While there is no conclusive evidence yet that G is varying with time, the possibility remains an open question. Future experiments and observations could provide more definitive tests of this idea, potentially revolutionizing our understanding of gravity and dark energy. As we continue our quest to understand dark energy, we'll now contemplate how neutrinos may hold the key to unraveling some of the biggest mysteries. Turning our attention to the subatomic world, we will discuss how neutrinos may be the key to unlocking dark matter and dark energy's secrets. Neutrinos are fundamental particles that are electrically neutral, weakly interacting, and possess a tiny mass. They come in three known types, also called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. One of the most intriguing properties of neutrinos is their ability to change from one flavor to another as they travel, a phenomenon known as neutrino oscillation. This oscillation implies that neutrinos have mass, albeit a very small one, and that the different neutrino flavors are not mass eigenstates but rather mixtures of them. The connection between neutrinos and dark energy lies in several theoretical possibilities. One possibility is that the energy density associated with the neutrino sector could contribute to the overall dark energy budget of the universe. While the known neutrinos are too light to account for the observed dark energy, the existence of sterile neutrinos which do not interact with the known forces of nature could potentially fill this role. These hypothetical sterile neutrinos could have masses and mixing properties that allow them to contribute significantly to the energy density of the universe. Another possibility is that neutrinos may interact with other components of the dark sector, such as dark matter or other forms of dark energy. These interactions could have subtle effects on the behavior of neutrinos, such as altering their oscillation patterns or affecting their energy distribution. Scientists can search for these effects by studying the properties of neutrinos from various sources, such as the sun, supernova, and cosmic rays. One of the most promising avenues for exploring the connection between neutrinos and dark energy is through cosmological observations. The presence of additional neutrino-like particles in the early universe would affect the expansion rate and the formation of structures such as galaxies and galaxy clusters. By carefully analyzing the cosmic microwave background and the distribution of galaxies, scientists can place constraints on the properties of neutrinos and other light particles. These constraints can then be used to test various theoretical models of dark energy and dark matter. The search for these elusive connections requires a combination of theoretical insights, experimental measurements, and cosmological observations. Shifting gears once more, next we will be discussing a mind-bending concept: how quantum entanglement can cause exotic energy to form. As we delve deeper into the quantum realm, we arrive at quantum entanglement and how quantum entanglement can cause exotic energy to form. Quantum entanglement is a bizarre phenomenon where two or more particles become linked together in such a way that they share the same fate, no matter how far apart they are. When you measure a property of one particle, you instantly know the corresponding property of the other particle, even if they are separated by vast distances. The connection between quantum entanglement and exotic energy lies in several theoretical possibilities. One possibility is that entangled particles can be used to create exotic forms of energy that violate the known laws of physics. For example, some theories suggest that entangled particles can be used to create wormholes or other shortcuts through space-time, which could be used to generate energy from distant sources. Another possibility is that entanglement can be used to manipulate the vacuum energy of space. The vacuum energy is the energy that exists in empty space, even when there are no particles present. According to quantum field theory, the vacuum energy is not zero, but rather is a fluctuating sea of virtual particles that pop in and out of existence. Entanglement could potentially be used to manipulate these virtual particles, creating regions of space with negative energy density. Negative energy density is a form of exotic energy that is needed to stabilize wormholes and other exotic structures. One of the most promising avenues for exploring the connection between entanglement and exotic energy is through experiments in quantum information theory. Researchers are developing new ways to create and manipulate entangled particles, with the goal of developing new technologies such as quantum computers and quantum communication devices. These technologies could also be used to explore the fundamental nature of entanglement and its connection to energy and space-time. The exploration of entanglement and exotic energy requires a combination of theoretical insights, experimental measurements, and technological innovation. Scientists are pushing the boundaries of our understanding of the quantum world, with the hope of unlocking new sources of energy and new ways to manipulate the fabric of space-time. Shifting our attention to yet another dimension of the space, we will investigate cyclic models and explain how a new universe is created after each cycle. Venturing further into the unknown, we come across cyclic models and how a new universe is created after each cycle. Cyclic models propose that the universe undergoes endless cycles of expansion and contraction, with each cycle giving rise to a new universe. These models offer an alternative to the standard Big Bang theory, which posits a single, unique beginning for the universe. In cyclic models, the universe expands and cools, eventually reaching a point where it begins to contract. As it contracts, the universe becomes denser and hotter, eventually reaching a point of maximum density before bouncing back into another period of expansion. One of the key features of cyclic models is the mechanism that triggers the transition from contraction to expansion. This transition, often referred to as a bounce, is a critical moment in the cycle where the old universe is destroyed and a new universe is born. The physics of the bounce is not well understood, but some theories suggest that it involves exotic forms of matter or energy that violate the known laws of physics. One possibility is that the bounce is triggered by quantum effects, such as the creation of virtual particles that exert a negative pressure, causing the universe to expand. Another key aspect of cyclic models is the mechanism that erases the memory of the previous cycle. In order for each cycle to give rise to a new, independent universe, it is necessary to eliminate any information about the previous cycle. This is a challenging problem, as it is not clear how information can be completely erased from the universe. Some theories suggest that the bounce itself is a chaotic process that scrambles information, while others propose that new physics beyond the standard model is needed to erase the memory of the previous cycle. Cyclic models offer a fascinating perspective on the nature of the universe and its origins. They suggest that the universe is not a one-time event, but rather an ongoing process of creation and destruction. While these models face many challenges and are not yet fully understood, they offer a compelling alternative to the standard Big Bang theory and provide a rich framework for exploring the mysteries of the cosmos. Our journey through these cosmic theories continues as we consider colliding brains and discuss how different brains interact with our own universe, causing its expansion. The 26th theory in our cosmic exploration involves colliding brains, where different brains interact with our own universe, causing its expansion. This theory comes from the realm of string theory, In string theory, the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. These strings can exist in more than the three spatial dimensions we experience, and these extra dimensions can be compactified into higher dimensional objects called branes. Branes are like membranes that can exist in various dimensions, and our universe may be confined to one such brane. The colliding branes theory proposes that there are other branes floating in the higher dimensional space, and these branes can interact with our own. When two branes collide, it can release a tremendous amount of energy, which could manifest as the dark energy that drives the accelerated expansion of the universe. The energy released during a brane collision can also create new particles and potentially alter the fundamental laws of physics within our universe. One appealing aspect of the colliding branes theory is that it provides a natural explanation for the origin of dark energy. Instead of requiring a mysterious, unchanging energy density inherent in space itself, dark energy arises from the dynamics of brane collisions, which can evolve over time. Furthermore, colliding branes could also offer an explanation for the origin of the Big Bang. Instead of starting from a singularity, the universe could have begun with a collision between two branes. The collision would have created a hot, dense state that expanded and cooled, eventually forming the universe we see today. However, the colliding branes theory is not without its challenges. It requires the existence of extra dimensions and branes, which have not yet been directly observed. It also needs to explain why the collision occurred at the specific time, and with the specific energy that would give rise to the observed properties of dark energy. Nevertheless, the colliding branes theory offers an intriguing possibility for understanding the universe's expansion and its fundamental origins. As these theories continue to push the boundaries of our understanding, we turn our attention to the holographic universe, a mind-bending concept that explores the very fabric of reality. Transitioning into more abstract realms, let's now consider the holographic universe and its implications for dark energy. The holographic principle suggests that the information content of a volume of space is not determined by the volume itself, but rather by the area of its boundary. This concept arises from black hole physics, where the entropy or the amount of information within a black hole is proportional to the surface area of its event horizon, not its volume. Extrapolating this idea to the entire universe, the holographic principle posits that all the information needed to describe our three-dimensional universe is encoded on a distant, two-dimensional boundary. This boundary is often referred to as the cosmological horizon, representing the limit of what we can observe in the universe. The holographic principle has profound implications for understanding dark energy, as it relates the entropy and energy density of the vacuum to the geometry of the cosmological horizon. In holographic models of dark energy, the observed value of dark energy is linked to the information content of the universe. The energy density of the vacuum, which is thought to be the source of dark energy, is determined by the number of degrees of freedom on the cosmological horizon. These models suggest that dark energy is not a fundamental property of space itself, but rather an emergent phenomenon arising from the underlying holographic structure of the universe. One of the key challenges in cosmology is explaining why the observed value of dark energy is so small compared to theoretical predictions. Holographic models offer a potential solution to this problem by relating the energy density of the vacuum to the size and geometry of the cosmological horizon. By connecting dark energy to the holographic principle, these models provide a new perspective on the nature of the universe's expansion. As we continue our exploration of the universe's enigmatic properties, the multiverse theory emerges. This theory opens up even more possibilities as to where the true source of dark matter and dark energy comes from. Venturing beyond our known universe, the multiverse theory posits that our cosmos is just one of potentially infinite universes, each with its own set of physical laws and constants. In this grand cosmic landscape, the true source of dark matter and dark energy might reside in the interactions between these different universes. One intriguing concept is that the gravitational influence of other universes could manifest as dark energy in our own. Imagine these other universes exerting a subtle yet pervasive pull on our own, causing the accelerated expansion we observe. This interaction could occur through various mechanisms, such as quantum entanglement or the exchange of hypothetical particles that can travel between universes. Another possibility is that the fundamental constants of nature, which determine the properties of matter and energy, vary from one universe to another. Universes with higher vacuum energy, for instance, could contribute to the overall energy density of the multiverse, influencing the expansion of our own universe through subtle gravitational effects. The multiverse theory also provides a potential explanation for the observed abundance of dark matter. It suggests that dark matter particles might not be entirely confined to our universe, but could instead leak from or interact with other universes, influencing the matter distribution and gravitational dynamics we observe. While the multiverse remains a highly speculative concept, it offers a compelling framework for understanding the universe's missing energy. Though direct empirical evidence for other universes remains elusive, scientists explore mathematical models and theoretical frameworks to test the feasibility of these ideas. By considering the possibility of interactions between universes, we can potentially unlock new insights into the nature of dark matter and dark energy, shedding light on the fundamental properties of our cosmos. As we seek to explain the universe's hidden gravitational energy that may be influencing our universe, another fascinating concept comes into play: gravitational ether. Transitioning from the mind-bending concept of the multiverse, let's explore another intriguing possibility: the idea that the universe is filled with hidden gravitational energy, often referred to as gravitational ether. This theory suggests that space itself is not merely an empty void, but is instead permeated by a subtle, underlying field of gravitational energy. In this view, the dark energy driving the universe's accelerated expansion is not an exotic substance like quintessence or phantom energy, but rather an intrinsic property of space itself. Imagine space as a vast ocean of gravitational potential, with ripples and currents constantly in motion. These fluctuations in the gravitational ether could exert a pressure on the fabric of spacetime, causing it to expand at an ever-increasing rate. One way to think about this is to draw an analogy to the old concept of the luminiferous ether, which was once thought to be the medium through which light waves propagated. Although the luminiferous ether theory was ultimately disproven, the idea of a pervasive medium influencing physical phenomena has resurfaced in modern physics in various forms, including the concept of gravitational ether. The gravitational ether theory faces several challenges, including the need to explain the origin and nature of this hidden gravitational energy, as well as its interaction with ordinary matter and energy. However, it offers a compelling alternative to the standard dark energy models and provides a new perspective on the fundamental nature of space and gravity. To test this theory, scientists look for subtle variations in the gravitational field across cosmic distances, as well as potential interactions between the gravitational ether and other forms of energy. By exploring the concept of gravitational ether, we open up new avenues for understanding the universe's missing energy and its profound implications for the cosmos. As we continue to probe the mysteries of dark matter and dark energy, another radical idea emerges: emergent gravity. Diving into even more speculative realms, emergent gravity proposes that what we perceive as gravity is not a fundamental force at all, but rather an emergent phenomenon arising from the collective behavior of other, more fundamental forces and particles. In this view, gravity is akin to the concept of temperature, which is not a fundamental property of individual atoms, but rather a statistical measure of their collective motion. The idea is that gravity emerges from the underlying quantum structure of spacetime, potentially linked to concepts like entanglement entropy and information theory. One prominent model of emergent gravity is Eric Verland's theory, which suggests that gravity arises from the tendency of systems to maximize their entropy or disorder. According to Verland, the force we experience as gravity is simply a manifestation of the universe's drive to increase its information content. This perspective challenges the conventional understanding of gravity as a fundamental force mediated by gravitons, the hypothetical particles that carry gravitational interactions. Instead, it posits that gravity is a consequence of the statistical behavior of microscopic degrees of freedom within spacetime. The emergent gravity theory has profound implications for our understanding of the universe's missing energy. If gravity is not a fundamental force, then the accelerated expansion of the universe may not require the existence of dark energy at all. Instead, it could be a natural consequence of the emergent nature of gravity itself. Testing this theory is a formidable challenge, as it requires probing the deepest levels of spacetime and understanding the interplay between quantum mechanics and general relativity. However, scientists are exploring various avenues, including studying the behavior of black holes, the cosmic microwave background, and the large-scale structure of the universe to find evidence for or against emergent gravity. As we explore these diverse theories, from the cosmological constant to emergent gravity, it is important to consider how future research will shape our understanding. Transitioning our focus to the horizon, future research and observational tests stand as beacons, guiding our quest to unravel the mysteries of dark energy and to rigorously test the multitude of theories we've explored. Central to these endeavors are ambitious space missions and ground-based observatories, each designed with the singular purpose of peering deeper into the cosmos and gathering unprecedented data about the universe's expansion history and the distribution of matter within it. One such mission is the Euclid satellite, managed by the European Space Agency. Euclid is designed to map the large-scale structure of the universe with exceptional precision. By measuring the shapes and redshifts of billions of galaxies, Euclid aims to provide a comprehensive view of the distribution of dark matter and the effects of dark energy on cosmic structures. Its observations will allow scientists to test various dark energy models, including the cosmological constant and quintessence, and to search for any deviations from general relativity that might indicate modified gravity theories. Complementing Euclid's space-based observations is the Vera-C Rubin Observatory, a ground-based telescope located in Chile. This observatory is equipped with a powerful camera that will conduct the Legacy Survey of Space and Time, a 10-year project to image a vast swath of the sky. The Rubin Observatory's survey will provide a wealth of data on supernova, weak gravitational lensing, and the distribution of galaxies, all of which are crucial for understanding cosmic acceleration. By combining these multiple probes of dark energy, scientists hope to break through the limitations of individual methods and obtain a more robust and reliable picture of the universe's expansion history. Moreover, these future experiments and surveys are not just about confirming or refuting existing theories. They also hold the potential to uncover entirely new phenomena and to challenge our fundamental assumptions about the nature of space, time, and gravity. The quest to understand the universe's missing energy is an ongoing adventure full of excitement, uncertainty, and the promise of transformative discoveries. As we anticipate these future revelations, let's wrap up this cosmic exploration, reviewing what we've discovered about the universe's missing energy. As we draw the threads of our investigation together, it's time to reflect on the sheer breadth of theories proposed to explain the universe's missing energy, each offering a unique perspective on this cosmic conundrum. From the enigmatic cosmological constant woven into the very fabric of space to the dynamic quintessence that evolves with time, scientists have explored every avenue in their quest to understand what drives the accelerating expansion of our universe. We've traversed the realms of modified Newtonian dynamics and modified gravity theories, entertained the notion of dark fluids with exotic properties, and even contemplated the unsettling implications of phantom energy and the possibility of a big rip. Our journey took us through the landscape of extra dimensions, the complexities of back reaction, and the potential revisions to the universe's age. We considered vacuum decay, mirror universes, and the elusive particles like actions, WIMP, and sterile neutrinos. Gravitational waves, inflationary epoch remnants, and the hypothetical fifth force each offered a tantalizing piece of the puzzle. The concept of dark radiation, a varying speed of light, and the vast string theory landscapes have all been considered. We've also touched upon time-varying gravity, neutrino oscillations, quantum entanglement, cyclic models, colliding brains, the holographic universe, the multiverse, gravitational ether, and emergent gravity. The quest to understand dark energy is far from over, and future research coupled with advanced observational tests promises to bring us closer to a definitive answer. Missions like the Euclid satellite and observatories such as the Vera C. Rubin Observatory are at the vanguard of this endeavor, poised to collect invaluable data that will either validate or challenge current theories. The implications of unraveling the nature of dark energy are vast, potentially revolutionizing our understanding of cosmology, particle physics, and the fundamental laws that govern the universe. It's a mystery that calls to the brightest minds and most advanced technologies, promising not just answers but a deeper comprehension of our place in the cosmos. So as we conclude, keep looking up, stay curious, and continue to explore the mysteries of the universe with us. If you enjoyed this cosmic journey, be sure to like this video, subscribe to our channel, and hit the notification bell so you won't miss out on future explorations of